Good morning friends. Last we discussed about the characteristic of photoelectric effect, and we also drew the graph of intensity versus stopping potential and also the frequency of incident radiation versus the stopping potential. Okay. Now there is the characteristic of photoelectric effect. In our study we discussed about that when the light of the sufficient frequency, that means the more than the threshold frequency incident on a photosensitive surface. So photoelectrons are emitted from this surface, and this photoelectrons forms the electric current that is known as the photoelectric current, and this phenomena is photoelectric emission. Okay. So here the necessity is that the frequency of incident light must be greater than some particular frequency for given substance, and minimum value of the frequency is known as the threshold frequency. Okay. Today we have to discuss about that. Explain for photo emission, the frequency of incident radiation should be greater than the threshold frequency. We have to explain this sentence. So how we explain it? Therefore, for different metal, the value of the threshold frequency is different. Already we discussed for alkali metal and also the cesium, potassium, rubidium, these are the alkali metal, while the magnesium, we also discussed the ultraviolet light is used to produce the photoelectric effect in magnesium. Okay. So here the selenium is more sensitive than the zinc and copper. So there is the more sensitive surface to produce the photoelectric emission. Okay. Now the same photosensitive surface gives the different response to light of different wavelength. If the wavelength, that means the frequency of the incident radiation change for given same photosensitive surface, so photoelectric emission is also different. Suppose we take the 2 or 3 same piece of the photosensitive substance, but the frequency or the wavelength of incident radiation are different. So photoelectric emission is also different. Okay. UV light produces a photoelectric effect in copper. UV light produces the photoelectric effect in copper, but the green and red light does not. So for copper photosensitive surface, the ultraviolet light can produce the photoelectric emission, but green or the red light does not produce the photoelectric effect because the frequency of the green and red light is less than the UV light. Therefore, it can't produce the photoelectric emission in the copper. Clear? Okay. If the frequency of the incident radiation is more than the threshold frequency, the photoelectric emission starts instantly, even if the intensity of the incident radiation is less. So this sentence suggests that photoelectric emission does not depend on the intensity of incident radiation. It is only depends on the frequency of incident radiation. For photoelectric emission, the frequency of the incident radiation must be greater than the threshold frequency. If the frequency is less than threshold frequency, it can't produce the photoelectric emission. If the intensity is any higher value, so photoelectric emission is not depends on the intensity of incident radiation, that is only depends on the frequency of incident radiation. As the radiation with the higher frequency than the threshold frequency incident on a photosensitive surface, so instantly the photoemission is stopped within the 10⁻⁹ second or less time. Okay. If the intensity of the incident radiation is less. Okay. Now, emission starts with the 10⁻⁹ second or less time. So, emission of the photoelectron from the photosensitive surface is instantly. Yes, the light will start to incident on it. So on the spot, that means within the 10 is to minus 9 second time interval, the photoelectrons start to emit from the photosensitive surface. Thus, the frequency of the incident radiation must be greater than the threshold frequency for given substance. So that is the explanation of this sentence. After that, the most important question for 2 marks, that is write characteristic of photoelectric effect. For 2 marks only we have to mention the characteristic. Already we discussed how the frequency is depends on, or how the stopping potential is depends on the frequency, and photoelectric current depends on intensity of incident radiation. With the graph we explained, so these 2 questions is also important for 2 marks. Next is, suppose the question is asked like this way, that characteristic of photoelectric effect. So here the 4 characteristics. First is that for given photosensitive surface, when the frequency of the incident radiation is more than threshold frequency, so photoelectric current is proportional to the intensity of the light. So first part explains that for photoelectric emission, the frequency must be greater than the threshold frequency. If the frequency is less than the threshold frequency, so photoelectric emission does not start. And as the photoelectric emission started, so the photoelectric current, that means the number of the photoelectron produced from the photosensitive surface, depends on intensity of the light. Intensity of light. Again, for given photosensitive surface, when the frequency of incident radiation is more than the threshold frequency, so photoelectric current is proportional to the intensity of incident radiation or the light. Now second, for given substance and given frequency of incident radiation, saturation current is proportional to intensity of radiation, but stopping potential is independent of intensity. So what this characteristic suggested? If the substance is fixed, given substance, and frequency of incident radiation is fixed, but this frequency is greater than the threshold frequency. In this case, how many numbers of the photoelectrons emitted, that means the photoelectric current, depends on intensity of radiation, but the stopping potential, that means stopping potential, that means the kinetic energy of emitted photoelectron is independent of intensity. So numbers of the photoelectron emitted by the metal is depends on the intensity of the light. But what is the kinetic energy of the emitted photoelectrons is independent of intensity of light. Now third, if the frequency of incident radiation is less than the threshold frequency, what's happened if the F is less than F0? So photoelectric emission will not take place. So photoelectric emission does not start for any higher intensity of the radiation. If the intensity of the radiation is any high, but the frequency is less than the threshold frequency, so photoelectric emission will not start. Now, the stopping potential, that means the kinetic energy, depends on frequency of incident radiation. Just in second characteristic, we discussed that the photoelectric current depends on the intensity of incident radiation, but the stopping potential or the kinetic energy is independent of intensity. So stopping potential or kinetic energy depends on frequency of incident radiation, but it does not depend on intensity of radiation. Now, fourth and last, photoelectric emission is photoelectric emission is independent of frequency, independent of intensity of radiation. It is instantaneous. It is instantaneous and take place within the 10⁻⁹ second or less interval of time. So photoelectric emission is not depends on intensity of light. It is only depends on the frequency of incident radiation, and condition is that if the F is greater than F0, that means the frequency of incident radiation is more than the threshold frequency, so photoelectric emission starts. So it does not depend on intensity of light. As the radiation having the frequencies more than the threshold frequency, so within the 10⁻⁹ second or less interval of time, the photo emission or the photoelectrons start to emit from the metallic surface. So these are the characteristics of photoelectric emission. Here we have to discuss about that. What is the effect of the frequency and intensity in photoelectric emission? Clear? After the discussion of the characteristic of photoelectric effect, the next question is that the failure of wave theory to explain the photoelectric effect. Or this question you also ask like that way. Why the wave theory of light cannot explain the basic features of the photoelectric effect? Right? We are going to discuss about that. Before it, again we revise the photoelectric effect. In photoelectric effect and characteristic, for produce the photoelectric effect, the frequency of the incident radiation must be greater than the threshold frequency. Clear? As the frequency increases, so kinetic energy of emitted photoelectrons, that means the stopping potential also increases. And as the intensity of the incident radiation increases, so number of photoelectron increases, emitted numbers of the photoelectron increases, that means the photoelectric current is also increases. Thus, the photoelectric current depends on intensity of incident radiation, while the kinetic energy of emitted photoelectrons, that means the stopping potential, depends on frequency of incident radiation. And third thing is that the photo emission of electron is instantly within the 10⁻⁹ second of incident radiation on a photosensitive surface. So within the 10⁻⁹ second, the photoelectrons are emitted from the surface. So keep in mind these three sentences to explain the failure of wave theory to explain the photoelectric effect. Now, as we consider the light as a wave. Wave, that means there is the electromagnetic waves made up of the electric and magnetic field. Already we learned in electromagnetic waves chapter. Light is electromagnetic wave made up of the electric and magnetic field. The phenomena like the interference, diffraction, and polarization can be explained by the wave nature of light. Already we discussed in chapter 10. We discussed the phenomena like as the interference, diffraction, and polarization by considering the light as a wave. Right? According to the wave theory of light, when the light is incident on a metal, the free electron will absorb the radiant energy continuously. So in photoelectric effect, as the light is incident on a photosensitive surface. So what's happened? What are the free electrons on the surface of a metal? Continuously absorb the incident radiation. Right? When the intensity of the incident radiation increases, so amplitude of electric and magnetic field also increases. Already we discussed about that. I is directly proportional to A square. A is the amplitude of electric field and magnetic field. That means as the intensity of the incident radiation increases, so the amplitude of electric and magnetic field also increases. Hence, the more energy will absorb by the electron. So here the amplitude of electric and magnetic field will increases. Therefore, the electron absorbs the more energy. Hence, the more energy will be absorbed by the electron. Thus, the maximum kinetic energy of the electron increases with increase in intensity of light. So as a result, what's happened? As the intensity of the light incident radiation increases, so the amplitude of electric and magnetic field increases. Therefore, whatever the energy absorbed by the electron on the surface of a metal also increases. Thus, the kinetic energy of this electron increases with increase in intensity of a light. Okay. A sufficient intense beam of any frequency should be able to impart the enough energy to electron so that the exceed minimum energy needed to escape from the metal. A threshold frequency therefore should not exist. So according to the wave theory, if the intensity of the light is increases, what's happened? The kinetic energy in form of absorbed energy of an electron also increases. Yes, the energy of the electron is much more than the binding energy, so electron can be easily escaped from the metal. Therefore, the threshold frequency is not important to escape the electron from the metal. Again, as the intensity of the incident radiation increases, so what's happened? The energy absorbed by the electron is also increases. Therefore, the kinetic energy of this electron on the surface of a metal is also increases. So this maximum or this minimum kinetic energy is needed to escape the electron from the surface of a metal. Therefore, the threshold frequency not exists. There is no importance of the frequency of the incident radiation according to the wave theory. But our result shows that result of the experimental photoelectric effect shows that to emit the photoelectron from the surface, the frequency of incident radiation must be greater than the threshold frequency. If the light is any intensity, whether it is any intensity, but the frequency is less than the threshold frequency, it can't produce the photoelectric effect. Thus, there is a first failure of the wave theory. So wave theory cannot explain the importance of the frequency to produce the photoelectric effect. According to the wave theory, the frequency is not important. Intensity of the incident radiation is important to emit the electron from the photosensitive surface. Well, according to the wave theory, second failure, according to the wave theory, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Now, whatever the waves is incident on the surface, so energy of the wave is continuously distributed on a wave. So when this wave is incident on the surface, so electron continuously absorb the energy. Therefore, to collect much energy by the electron, it takes place the more time. As a very large number of the electron absorb the energy. So as a result, the large number of the electron on the surface of the metal at the same time absorb the energy. Therefore, the energy per electron will be very less. Again, according to the wave theory, absorption of energy by electron takes place continuously over the entire wavefront. When the wave is incident, that means the wavefront is incident. Therefore, the large number of the electrons on the surface of a metal at the same time absorb the energy. Therefore, the absorbed energy per electron will be very less. Is very less. so that the electron take the more time to escape from the metal. So wave theory suggests that the emission of the electron does not take place instantaneously. That means the instant. It takes some time after the incident of the radiation on a surface of the metal. When the electron gets the energy is more than the required minimum energy, at that time that can escape from the metal. So the energy of the wave is in form of a wavefront. When the wavefront is incident on a metal, so a large number of the free electron on the surface of a metal at the same time absorb the energy. Therefore, the absorbed energy per electron will be very less, so that the electron take the more time to escape from the metal. So this conclusion is also contradictory to the experimental result, in which the electron emission start within the 10⁻⁹ seconds. But the result of the photoelectric effect shows that the emission of the photoelectron take place within the 10⁻⁹ seconds. That means the instant emission of the electron take place. So thus the wave theory is unable to explain the basic feature of photoelectric effect. So that is also most important question for the 2 marks. Explain the failure of the wave theory to explain the photoelectric effect. We start from this as we consider the light as an electromagnetic waves that is made up of the electric and magnetic field. Okay. Phenomena like the interference, diffraction and polarization can be explained by wave nature of light. According to the wave theory of light, when the light is incident on a metal, the free electron will absorb the radiant energy continuously. Because the light is continuously incident, therefore the electron on the surface of a metal continuously absorbs this energy. Clear? Okay. When the intensity of the incident radiation increases, so what's happened? The amplitude of electric and magnetic field also increases. Hence, the more energy will be absorbed by the electron. Thus, the maximum kinetic energy of electron increases. So, the energy absorbed by the electron becomes the maximum kinetic energy of the electron. Increases with the increasing intensity of light. So here the wave theory suggests that as the intensity of the incident light increases, so the kinetic energy of the electron on the free surface also increases due to the absorption of energy. The sufficient intensity of any frequency should be able to impact enough energy to electron. Thus, the wave theory suggests that the sufficient intense light is able to give the more energy to the electron. Therefore, frequency is not important. So that the minimum energy needed to escape from the metal. So when the energy of the electron is more than the needed minimum energy, at that time the electron can escape from the surface of metal. Thus, the frequency is not important. But the experimental result of photoelectric emission suggests that for photoelectric emission, the frequency of incident radiation must be greater than the threshold frequency. Any intense light having the frequency less than threshold frequency can't produce the photoelectric emission. So there is the first failure of wave theory. Second, according to the wave theory, absorption of energy by electron takes place continuously over the entire wavefront. Right? And at a time, the large number of the electrons on the surface of a metal absorb the energy. Thus, the energy per electron will be very less, so that the electron takes more time to escape from the metal. But our experimental result shows that the emission of the electron is instantly. Within the 10⁻⁻⁹ second, after the emission of incident radiation, the photo emission is started. So thus the wave theory cannot explain the photoelectric emission, but the basic feature of the photoelectric effect. Clear?